Hi, everyone. Welcome to last review session. Woo. So your final is tomorrow if you're in the 1240 class at 10:30. I will be there bright and early with your exams at 10 o'clock. So yay. And if you are in the 3 o'clock class, then you have your exam on Monday at 10:30 as well. And but this will be the last review I do for this, just so that it's like fair for both classes. Right, you'll have this review, and then if you're in the 3 o'clock class, you can watch this again, but I will not do anything extra. So this will be the last time you have to hear my voice. And then, yep, it'll be in your classroom at 10, the classroom, like ILCB 226 at 10:30. Yep.
Curiosity.
Yep, go ahead.
Do you happen to know if there's another final beforehand, or can we go in early?
I believe the one beforehand is 8 to 10, and then there's like a 30-minute transition, and then you do the 10:30 to 12:30.
Sure.
So I'll be right outside the classroom at 10 o'clock for when that last one gets out. I do not know if you have to stay the whole time. I'm assuming you will have to, just based off of how he's ran his in-class exams. But I'm assuming you're gonna need most of the time. So bring some scrap paper if you want to draw a picture. You will not be given the formulas from the previous exam, I believe. I think you have to still know all of your formulas, but any like constants or any conversions, we will make sure that that is on the exam. And if you think that you need something, right, just raise your hand and I'll come and answer it, and I'll check with Dr. Lindahl to make sure that it's something that's needed. I have not seen the exam, so I do not know like how many questions or what's on it. So that'll be a adventure for both of us tomorrow.
Do you think it'll be set up similarly though, like with the true and false at the beginning?
I believe so. I think he's going to do it where it's right, think of it as an exam and a half, right, for your final, because it's 150 points. So probably 8 to 9 true false would be my guess, and then like 10 to 12 actual questions. And that should take up probably 2 hours.
From what he told me is that he's sectioning off each module, so it'll all be broken up, and we'll know when we're changing content in a sense.
Oh, that's very nice of him. Um, any other logistic questions about the exam? I'm sure 1240 is excited for this to be over. 3 o'clock, your classes, you're almost done. I promise you're almost there. Okay, I have a couple of questions in the chat that people wanted me to go over. So let me just pull them up real quick and then we can get started. The first one is going to be exam 7, question B8. So I just have to grab that. I might have to switch my cameras. Okay, so exam 7, question B8. This is okay. And this was one of the questions where you had to find which of the statements were correct. So statement 1 said, this. So for this one, right, we're looking at the equation given, which is chromium hydroxide and bromine and hydroxide ions are going to form the chromate ion, the bromine ion, and then water. So the first thing you need, or the first statement says, is the CrOH3 is the reductant. So we want to see if that's true or false. So if we're looking at this reaction, we're going to look for the oxidation number of the chromium ion. We know that in our oxidation numbers, oxygen will always be -2. So in this case, this oxygen is -2, but we have 3 of them. So we have a total of -6. And then our hydrogen is always going to be +1, but we have 3 of them, which means we have a total of +3. So overall, this guy is -3 in its charge, right? That hydroxide ion is -3, which makes sense, right? And it should be a -3 if we have 3 of them, because hydroxide has a -1 charge. So if you have 3 of them, the total is going to be -3, right? So that checks out. There's no overall charge of the chromium OH3, so we need to have a neutral oxidation states of our atoms. So since we have -3 from the OH-, that means that chromium has to be +3. Any questions on those oxidation numbers? Alrighty. So then if we look over at the chromium on the product side, this time we have a charge of -2. Again, oxygen's going to stay -2, but we have 4 of them. So we're going to have a total of -8. And since we have a total charge of -2, we're going to say that whatever that oxidation number of the chromium is going to be X, plus -8 has to equal -2. So if we solved for this, we would say that X is equal to +6, which means that chromium has to be +6. So as we go from +3 to +6, are we getting more positive or are we getting more negative? Yep, we're getting more positive. So is this oxidation or is this reduction? This is oxidation. So if something's going through oxidation, chromium is the thing that's being oxidized. So is chromium hydroxide is the reductant? Is that true or false? Yes, this is true. Someone said it in the this is true because the chromium is what is getting oxidized, which makes it the reductant. And right, someone asked if they're the coefficients in front. These do not matter. That's just balancing your elements, and it overall balances the charge. But since this is already balanced, the coefficients do not matter. Okay. In order to find out if question or statement 2 is correct, you do need to balance this equation. Unless someone has a different way of saying how much is added. But essentially, I would break this apart into 2 half reactions. So I would do your chromium hydroxide and your chromium or your chromate ion, and I would do your bromine and your bromide ion.
For the bromine and bromide, could you technically look at the overall charges and see that there is a n equals 6 for that specific set?
Yeah, so that's what I would personally do, right? If you're looking at the chromium and the chromate like half reaction, that one's going to get really complicated. But if you look at the bromine, you automatically start by saying, okay, there's 2 bromines on my reactant and 1 on my product, so I need a 2 in front of here. right, if you go through balancing in a basic reaction, you don't need to balance any oxygens, you don't need to balance any hydrogens, you don't need to balance with hydroxides because we just have bromine and bromide. So here you could balance your electrons directly. Since we have 2 negative charges on our products and 0 on our reactants, we would add 2 electrons to our reactant side. But we see from the balanced chemical reaction that we're given that bromine has a 6 in it. So we know that we need to multiply this by 3 in order to get to 6. So 6 electrons there, 3 bromines, and 6 bromides. This points us saying that N is equal to 6 because we know that that matches the balanced equation. So you can just stop there and say that this is true. And then for the last statement, the reaction was carried out at a pH of greater than 7. We have hydroxides in our balanced overall equation, so that's going to tell us that this is also true. So in this case, all statements were true.
Would we have to calculate like the negative log for the hydroxide ions?
In this sense, or like at any time in the exam?
Just to like find the pH for the third statement.
You are not given any concentrations of your hydroxide. So I don't think you would be able to find the negative log because you would need a concentration in order to do that. So in this case, I think you would just have to like look and see, okay, I know that this is OH minus, or there's OH minus present, which is going to make it basic.
Thank you.
Yep. If there was only H plus in the chemical reaction, then it would be a pH less than 7 because you have H plus, which is going to bring it down.
How is
Question.
the first statement true if it's oxidizing?
So the chromium is going through an oxidation, right? It's chromium is getting oxidation, which makes it the reductant. That ending changes, right? If something is going through reduction, it is the oxidant. Right? If it's the oxidation reaction, it's the thing that's causing the reducing. And if it's the reduction reaction, it's the thing that's causing the oxidation. Do you see the difference between those two?
Yes, I do. Thank you.
Yep, absolutely.
When we're balancing in a basic solution and we're adding the OHs, we have to add them. Like if you, let's say you add 5 to one side, you have to add 5 to the other side automatically, correct?
Yes. If you're balancing your hydroxide, however many you add to your reactants, you have to add to your products.
But you would only add the H pluses accordingly to balance after that one step, you add H plus only where you need to balance out H's, correct?
I balance
you
my
can't split
equations where you do the H plus first, and then you neutralize with the OH minuses.
Okay, so you do normal non OH and H, and then you add then H2O to balance out O's, and then you do the H or the H pluses, then the OHs.
Yes. Yep.
Okay, so I was doing it the opposite way.
Yeah.
Makes sense now.
Yep. Because then that makes it, if you do it that way, then if you're doing it in an acidic reaction, you can stop at those H pluses. But if you're doing it a basic, then you add that extra step of the hydroxides.
So the extra step happens afterwards.
Yes. Yep.
Okay, thank you.
Yep. Absolutely.
Going back to statement 3, is the OH the one on the reactant side?
Yes.
Okay, thank you.
Yep. Anything else on this question? Okay, great. Okay, and then I had another question for exam 1A. Oh, everyone wants 1A. Okay. So the next one we're gonna do is exam 1A. Question A9. And this is alrighty. So for this one, we have concentrated aqueous HCl has a molarity of 11.7 moles over liter and a density of 1.20 grams per centimeters cubed. What is the molality of the solution? So for this question, what I usually do if I'm ever like doing this unit conversion stuff is I'm going to say, okay, I have 11.7 moles over liters, right? This is molarity. Let me make this a fun color. You have 11.7 moles over liters, which is molarity. And then what is the top portion? Is that moles of what? Yep. Someone said HCl. So this is, yep, moles of solute. And this is going to be liters of what?
Solution.
Yes. Yep. Okay. For our density, the thing to note here is that centimeters cubed is going to be milliliters. So that centimeters cubed is just milliliters. And this is going to be, this is both going to be of the solution. And then lastly, we have molality, which is lowercase m. And that's going to be what?
Moles of solute over kilograms of solvent.
Good. Awesome. Okay, so the big thing that we need to note here is that we need to get our solvent because we are given solution for everything else, but we need to get to that solvent portion for our kilograms of solvent for our molality. So anyone have an idea of how we're going to do this?
We could use our density to cancel out our liters. So change the 1.20 grams per milliliter to grams per liter. Would we be able to do that?
I like your thoughts, but there's an easier way that we can do that. We can cancel out those liters. So when we're given molarity, you can always assume you have 1 liter of your solution. So if we have that, we can say that in 11.7 molar solution, right? Moles over liters. If we have 1 liter of this, this means that we have 11.7 moles of HCl. Okay, any questions? Any questions why we can assume that? Awesome. Okay. So if we have 1 liter of that, that automatically knows that we have 11.7 moles of HCl. So that solves this portion up here. We know that this is going to be 11.7 moles. The problem is that we need to know how many grams of your solvent you have and how many grams of your solute you have. How can we get to grams of our solute?
Just multiply by the molar mass.
Yeah, awesome, right? We can take our 11.7 moles of HCl and use our molar mass to get to our, that should be 35.45, 36.45 grams HCl, I think is correct. Yes. Okay, so then this gets us to $426.465 grams HCl. Okay, so that's how many, this is our solute. So now we need our solution, because then we can say that solution is equal to your solute plus your solvent. And then we can just cancel out that solvent. So how are we going to get to our grams of solution? Yep. So next thing we're going to do is, right, again, assuming 1 liter, we're going to say we have 1 liter of our solution. This is where we can use our density. We can say that 1 liter is equal to 1,000 milliliters. And then 1.20 grams is equal to 1 mil. So we end up with 1,200 grams of solution. And now we can subtract and say that 1,200 grams minus 426 we end up with 773.5 grams of solvent. And so how do we find our molality? What goes on top? Yep, we'll put our 11.7 moles over our convert this grams to 0.7735 kilograms. And we end up with 15.1, which does match the answer from the exam. Questions there? Does this make sense how we use kind of like a roadmap to figure out what we need and what we had and what we needed and all that fun stuff there? Feel good? Great. Okay, and then, okay, great. Yep, I think the best thing that you can do during your exam is just write out your roadmap, make sure you know what each of your units means, and then you can figure out what path you need to take and say, okay, I know I need to convert this to this. What do I need in order to do that? Okay, the next question is going to be also from exam 1. This will be question A12. So it says, okay, so for this question, we have the heat of fusion of water at 0 degrees Celsius is 334 joules per gram. How many joules of energy are needed to convert 2 moles of water at 0 degrees Celsius into ice at 0 degrees Celsius? Okay. So in this case here, what we're looking for is the heat of fusion. So this is very similar to the heat of vaporization that you see when water boils, but this time it's just water freezing. So Q, the equation you're looking for here is Q is equal to M times the delta H of fusion. What is M here and what units is M in? Close. Moles would be N actually. Mass is, or M is going to be mass. So this is going to be the mass in grams. If it were moles, it would say N times the delta H of fusion. Okay, so we need mass for this one. And yep, so usually it's given as moles, but in our question, we're giving it as grams. So that's why, you want to use mass instead of grams, or mass instead of moles. Okay, so we can solve for Q but we need mass first. So how do we solve for mass given 2 moles of water? What do we use to convert to grams? Perfect. Yep, we're going to use 1802 because for every 1 mole of H2O, we have 18.02 grams of H2O. So we have 36.04 grams. We're given the delta H of fusion, so we can just plug that in to our equation and solve for Q. Q is equal to 36.04 times 334 joules over gram. So Q is Good. So great question. So the delta H of fusion, for this case is going to be negative. And can someone tell me why? Good. It's freezing. So if it's freezing, right, because we're going from water into ice at 0 degrees Celsius, that means that we are releasing heat, right? This is an exothermic reaction if we're going from water to ice. And so since it is an exothermic reaction, we need the negative version of this. So when we solve for Q, we should have said Q is equal to negative 334, which makes the Q 12 kilojoules. Or negative 12 kilojoules. And your answer choices, he asked for how many joules of energy. So that's why negative 12 is not the answer, because we have negative 12 kilojoules, right? It should be negative 12,000 joules. Yes, heat is being released. Anytime, so if you go from solid to liquid to gas, this is all endothermic. So heat is absorbed. And as you go this way, this is all exothermic. So heat is being released. Yep, someone asked about 14 on this exam, so just we'll stay on exam 1A first, and then we'll switch to exam 1C. So exam one, question A14. This one is referring to the phase diagram. So it looks like this here. Okay. So statement 1 says region A is where the molecule is a liquid. This is point Y is called triple point. And at sea level, the molecule freezes at 87 degrees Celsius. Okay. So just to quickly review this, these are your solids, these are your liquids, and this is your gas. Those are the regions, they will always follow those regions. This is the triple point. This is the critical point. And any black line that you see here, so this guy, or this guy, all of those are at equilibrium. And they are phase changes. Oops. Right, so all those blue lines are phase changes. So that would make statement 1 true. Sorry, statement 1 is false. Statement 2 is true. Statement 3, they're saying at sea level, the molecule freezes at 87 degrees Celsius. At 87 degrees Celsius is this point here that they're referring to on the exam. At that red circle that I just had, it is already frozen. It is not freezing, right? It's not on a line of going back and forth between solid and liquid. It is simply just frozen. And so that since it's not freezing or in the act of freezing, it's already ice or already solid. This one is false. And that's why that one is false. Does that make sense of those statements and this diagram?
So is it in between the curves is what that phase change is? Like in the solid section, it's like frozen, and the liquid section is liquid, and then gas
Yep.
section is gas molecules.
So in this, like this reason here, right here, it's freezing and thawing, or like thawing and freezing as you're along this line here. That's in the act where it would be freezing or whatever, freezing or melting. Right, this point here, it's either boiling or condensing, right? So if they said at whatever this temperature is, 120, right? At 120 degrees Celsius, this sample is boiling, that would be a true statement because you're on that phase change line.
Okay, thank you.
Yep.
Could it be like either or though? Like it could be boiling or condensing?
Yes, right. It could be either or, but in any case, it's at equilibrium. They're both happening. So if they're saying it's
Oh, okay.
boiling, yes, it's boiling. If they're saying it's condensing, yes, it's condensing because both are happening.
If they say you're at that pressure, but you're going to a lower temperature, would it would just be one of them, right? Like let's
Yes,
say,
right.
yeah.
If they said this was, right, this was 100 degrees Celsius. So at this point here, you are simply just a liquid.
But if it said it started at 100 and moved to 130 degrees, what would it?
Yep. So that's a great question, right? If it started here and we're going to end up here, what happened?
So it condensed, right?
It's going from liquid to gas. So what is it doing?
Oh wait, why am I blanking out? It's evaporating.
Yes, it's evaporating or boiling. Yep.
Okay, thank you.
Yep. Great questions. Anything else on this little diagram? Cool. Okay, someone asked for C8 from exam 1. I'm gonna read this. So C8 says the concentration of lead in a water supply is 27 parts per billion. What would this concentration be in terms of molarity? Assume a density of 0.997 grams per mil for the solution. I'm going to guess that parts per billion will not show up. If it does, I sincerely apologize. But I think that that's like the only time you really talk about parts per billion. And I think if he's going to ask a question, it's going to be more about molarity or molality. We don't really work with parts per billion, so I don't think he would put that on a final. So I'm just not going to do that because I think there's other questions that we could do instead that are going to be better for your knowledge. So I apologize to the person that wanted that. Okay, someone. Let me read. There are a couple of people are saying stuff, so I'm just going to look and see which ones I think are going to be most beneficial. Okay, we're gonna do exam. Exam 3, question B8. Okay. This one is asking or saying that the equilibrium constant Kc for the decomposition of phosgene COCl2 is 4.63 times 10 to the negative 3 at 537 degrees Celsius. The reaction is COCl2 forms carbon monoxide and chlorine gas. And we want to find the equilibrium partial pressure of phosgene in ATM if the reaction was started with pure phosgene at 0.760 ATM. Does anyone have an idea of how we're going to do this question? Or what's needed or something that we're going to have to do along the way?
Set up an ice table, maybe.
Yep, we'll definitely have to set up an ice table. Is there something that we can't use interchangeably here? Or is there something that we need to change?
Should we change the ATM to concentration?
Yeah, we can do that. So, right, that's either one is good here. We are given Kc is this value here, but we're given a reaction initial value in pressure. So Kc is for concentrations, but pressure is for Kp. So you can either use the equation that relates Kc to Kp, or you can use PV is equal to nRT to get to the number of moles, and then you can assume 1 liter, and then you can have your concentration, and you can use it that way. Personally, I think that way is better, just because I always remember PV is equal to nRT, but I never remember the conversion between Kc and Kp. So that's totally up to you. But I'm going to use PV is equal to nRT. And we're going to solve for N, which is our moles. So that was going to be N is equal to PV over RT. Our pressure is 0.760 ATM. Our volume, we can just say is 1 liter. Since that's not given, you can always assume 1 liter. Our R value is 0.08206. In temperature, you need to convert to Kelvin, so that's gonna be 537 plus 273. That's 810 Kelvin. So we get that N is equal to 0.0114 moles. We can again assume 1 liter, so we can get 0.0114 molar. And that now becomes the start of our ice table. So how do we fill in the rest of our ice table? Do we have any starting product? Do we have any starting products? Nope. What is our change?
Our change will be a negative, positive, positive.
Awesome. Right, we have no coefficients, so this can just stay minus x, and plus x. So this is our value at equilibrium. We can then plug this into Kc. To write this out, this would be carbon monoxide over Cl2 all over CoCl2. And Kc is we end up with that. In this case, I would not use the assumption. It is not 2 orders of magnitudes different, so I would distribute all of this and then do the quadratic formula. Just for the sake of time, since I know this is only an hour, when you get x will be a value. We'll call it a smiley face. This will be in moles. In order to, this will be in molarity. You're going to multiply by your 1 liter to get smiley face in moles. Should still be smiley face. You will then plug in your smiley face in for N. So P is equal to smiley face times RT divided by V, and that'll be your pressure. So, right, you have to undo to get back to pressure what you did to get out of pressure. And that'll be your answer for this question. Does that make sense how you would finish it off? I just don't want to have to write everything out. Just that we can ask a couple more questions before we all leave. Okay, and then last one that we'll talk about is exam 3, question D9. This one is pretty similar to one we just talked about. It's just asking for the partial pressure. So for this question, I'll just kind of walk you through how you would do it. So they have CS, CO2, and 2CO gas. They're saying that at 700 Kelvin, the total pressure of both gases combined is 4.50 atm. If Kp is equal to 1.52, what would be the partial pressure of CO? So what you would have to do here is that if you were to write out your reaction, and form an ice table, you know that, right, this doesn't matter. And at equilibrium, whatever X and Y are, those are going to equal to 1.52. Okay, so Kp is going to be set up where CO squared over CO2. Kp is equal to 1.52. I'm sorry, this is not equal to 1.52. This is equal to 4.50. So 1.52 is equal to whatever X is, right? That could be carbon monoxide, we'll call it, over 4.50 minus X, right? Because partial pressure means is the P total is equal to the sum of P1 plus P2 or PA plus PB. So in this case, 4.50 is pressure of CO plus the pressure of CO2, right? So whatever X is, right, because that's the pressure that you're trying to solve for. You're trying to find what the partial pressure of CO is. X would be that value, where CO2 would be whatever is not made up, or everything else, right, that is not made up from that CO gas.
I also want to ask a question. For your 1.52 is equal to X squared, would that be 2X squared?
So that depends on how you want to define it. So how you would set up your ice table, right, is if you're just going to do this normally, right, this would be 0. This would be plus 2X and end up as 2X, and this would be minus X, right? Okay. So you could set it up so that your pressure of CO is just X, which means that your CO2 would be half of X, or you can plug it in this way where you now say that this is 2X, and that way but you just need to know that your concentration is 2X, right? So you can solve for X and get CO2 directly, and then multiply by 2 to get to the concentration of CO. Does that make sense? Okay, awesome. Yep. So you can either do X or 2X. It just is depending on how you're going to define it. And then once you find what X is, then you can divide that by your total pressure. And so partial pressure would be the pressure of CO2 divided by pressure total.
If we decided to do the 2x and the x for the equilibrium, would the denominator look different in that KP equation? The 4.5 minus x, would that change, or would it still be 4.5 minus x?
It would still be 4.5 minus, it would be minus 2x this time, because you're defining whatever that, right? You're saying that CO makes up 2x. That's what it is. So 4.5. So in order to find whatever CO2 is, you need to subtract out all of 2x, all of whatever that carbon monoxide gas occupies.
So for that equilibrium problem, we're disregarding CO2 in a sense, or that's what I'm kind of still confused about.
No, so you're still taking that into consideration, because we're just saying that
Oh, I
X
think I got it.
here, yeah, X here is 2 times the pressure of CO2, right? So whatever CO2 is not making up, that's where this portion comes in. If you write 1.52 is equal to,
Yeah, sorry, I got it now.
yeah,
My brain
2x.
wasn't working.
Yep, right, that's still making up 2x. So now it's still, right, you still have to subtract out that other portion. So that would still be x.
Yeah.
Right, it's thinking of this here where you're saying this is 4.50. This is, you can either say pressure of CO is equal to x or 2x. So either way, it's just going to be, right, whatever 4.50 minus x or 4.50 minus 2x is going to be equal to the pressure of CO2. I know it's kind of hard to not like do it fully, but maybe you can try this one on your own again now. Okay. I will stick around for like 2 more minutes if there's any like really rapid fire questions you need, where it's just like strict concept ones and not worked out problems. But I'll say my
Go
spiel.
over
Yeah, go ahead.
the concept of what we were talking about yesterday with the affecting the pH in a sense to where that second molecule is both components of a strong acid and a strong base, so it wouldn't affect the pH.
Yes. Yep. So whenever you're adding, so we talked about one question yesterday in the review session, trying to find the pH of something, and they added potassium nitrate. Whenever you're adding a salt to your solution, it'll either be a neutral salt, a basic salt, or a acidic salt. If you can break this salt into its 2 components and say, what did this come from? In terms of potassium, this is going to come from KOH. In terms of the nitrate, this is going to come from HNO3. This is a strong base, and this is a strong acid. Since we have 2 strong things, these will completely dissociate, and so they essentially cancel out. So there is no affecting pH because there's no additional equilibrium that we need to worry about. This will happen for any neutral salt you add to a solution. And this kind of goes back to your solubility rules as well. So anything that's in a group 1, anything that is, I think what am I looking for? Any nitrate, the nitrate is always going to work, right, is going to be soluble. Right, your ClO4 minus is always going to be soluble. In those instances there, they will always have no effect on pH, and it's going to contribute in the question we talked about yesterday. It's just going to contribute volume, so it's diluting your solution essentially and just creating spectator ions.
Would the pH of that though be 7 since they both cancel each other out, or no?
Yes, in this case, if you just had a solution of this, it would be pH of 7.
Okay.
Yep.
Does a strong base cancel out the strong acid, and then same thing with like weak base and weak acid?
No. So if you have a weak acid and weak base, then you then have to look at which one is the stronger of the two. So you want to compare your Kas of the two or your Kbs of the two, right? You'll be given probably a Ka of something that's 1.5 times 10 to the negative 6, and your Kb of the base is 1.5 times 10 to the negative 6. Right? You can't compare apples to oranges. You cannot compare Ka to Kb. You have to convert one of them to the other and can look at those that way. And whatever is closer to 1 is the stronger acid.
Okay, thank you.
Not the stronger acid, the stronger component, if you convert to A or B.
Well, if we had a weak component and a strong component, then would it affect the pH?
Yes. Yep. So if you had something where it was NH4NO3, this breaks apart into NH4 plus and NO3 minus. This came from NH3. This came from HNO3. This is a weak base. You now have a equilibrium you're fighting with, and that will cause a shift in the pH. But this NO3 minus still hangs out as a spectator ion.
So the spectator ion will still just only contribute to volume.
Yep, it'll still only like this portion here will still contribute volume to your reaction, but you will have a secondary reaction of another equilibrium being established when you add it as well in this case.
Thank you.
And
I had a-
this-
Do you think you'd
This
ask
would
something
be-
like this?
I don't think so. I think that gets very complicated because it's usually ends up with the common ion effect. And so you have to look at, you end up in a scenario where you have A plus B, or sorry, A going to B plus NH3. So then you end up in an ice table where you have 0.5 starting of this and also 0.25 starting of this, right? And so then you have to solve for Q, and then it ends up where this is minus X and plus X and plus X. And so now at equilibrium, you have this, this, and this, and it gets complicated with the minuses and plus X's. It could happen, but I think he might ask you more straightforward questions.
I had a question on the relationship between the boiling point and the molarity, if they give us molarity.
It's like, what is the relationship? Are you asking?
Oh yeah, what's the relationship? Like if
So
it's high-
so the higher the molarity, the higher the boiling point has to be. The more stuff you have in solution, the harder it is for it to boil.
what about for like pure water, like non-ionizable things?
Yep, so still same thing. Pure water will always have the lowest boiling point. Anytime you add something to solution, it'll increase its boiling point.
Thank you.
Also with the like KP, KCs and all that, the bigger the KP, the slower the reaction is, and the smaller the K value, the faster the reaction is, or it goes to its full extent.
In terms of capital K and equilibrium, we're not
Yeah.
looking at it's when you have capital K, you're looking at, is it product favored or reactant favored? So if it's really big, then you have a lot of products and you say it goes to completion. If you have a small KC or small K value, then you have reactant favored and it's not going to completion because most of your reactants are going to stick around.
Gotcha.
Alrighty, well, It has been a wonderful hour tonight. It's been a wonderful semester. I hope this was helpful. Thanks for coming around before exams and seeing me during the week if you came on the off weeks. If you have any questions between now and the exam, my email should be open. I'm going to bed after this gets posted, so maybe not tonight, but definitely tomorrow morning before the exam. And this was recorded and I will post it right afterwards in case you need to do any last minute studying. But make sure you have a good night's sleep. Make sure you have a big breakfast in the morning and you do all of your fun study things and say your fun study rituals before a final. I'll be there. I'll see your smiley faces for the 1240 class. If you're doing this on Monday, do all those same things, but just on a Sunday night instead of a Thursday night. And I'll see you then. Good luck. This has been a great semester. Thanks for sticking around. Please let me know if you ever need anything. I'm happy to do anything else for you. I enjoy teaching, so. Have a great night.